Good afternoon, everyone. I'm Chieko Umetsu. My presentation is the first part I'll present and then switch to Soyoka, and she's going to present the empirical part of our research. First introduction. So this figure shows that low-income countries tend to have high change in precipitation and also the temperature changes. And this figure also shows that more dependent, if countries are more dependent on agriculture, and similarly the change in precipitation and temperature is very high. So there's a justification for doing a research on the impact of climate change on those low-income countries. And impact of the climate risk will go through two components. First is the risk management strategies, and another is agricultural productivity. The first one, risk management strategies, the expected utility theory suggests that the risk-averse individuals prefer reducing volatility at the cost of return in a risky environment. And many sub-Saharan Africa countries promote crop diversification as a national policy. While current adaptation is insufficient relative to the recommended climate risk mitigation level, site-specific evidence is pretty limited. And for the agricultural productivity, climate risks may reduce productivity indirectly also. And adaptation measures induce conservative, low-risk, low-return technologies. So the past literature shows the existence of ex-ante effects of uninsured risk. For example, risk hedge investment, asset portfolio with low-return liquid assets, and livelihood diversification, and human capital investment. And Chen and Gong decompose the impact of climate change on crop yields into total factor productivity and agricultural input. This is on the productivity side. And the case of there's a research done by Aslan et al. In Zambia, and it resulted in the existence of crop diversification in case of climate change. But our findings is not consistent with this Aslan result. So this paper examines the impact of climate risk on farmers' risk management strategies and agricultural productivity. And it combines national representative household level 2020 and 21 data from Zambia with high resolution meteorological data for 59 years. And we defined a rainfall risk index and related to agricultural decisions and quantified the yield changes due to risk management strategies. Our research shows for given stationary climate, there's no evidence on risk diversification in terms of crop production in agricultural production. And 20% low maize yield in high climate risk regions. And there was an underinvestment in fertilizer as the main source of yield loss. And farmers increased hybrid seed usage. As you know, Zambia is divided into 4 climatic zones. One is Region 3 and the north, which receives 1,500 millimeters. And the Region 2A is 800 to 1,000 millimeter, 1A. 2A is in this green part, and also the 2B with sandy soil. And the Region 1, less than 800 millimeter, which is shown in the red, this is the drought-prone areas. So this is the seasonal calendar, cropping calendar in Zambia. Most of the country's agriculture is rain-fed, and rainy season starts from November and go through April. And major agriculture activity is going on this period. And dry season is May, October. And agriculture is limited to winter maize and vegetable production on wetland and riverbanks. So during the rainy season, starting from November, planting, weeding, and harvest starts from March, April, May through June. So this is a graph based on the crop focus survey of Zamstat, and the left-hand side graph shows that the maize production is predominantly done by small-scale farmers in white bar. This is the medium size farms, and the right-hand side shows that most small-scale farmers cultivate 1 to 4 crops in the farm, and the number of crop increases when the farm size increases. So maize production is highly fluctuates with precipitation conditions. Even though the maize fails, millet and sorghum is still used something. So, but the maize is pretty vulnerable against the rainfall fluctuations. And the government tried to put the input support subsidy program and give farmers subsidized fertilizer. And agriculture credit is very limited to contract farming and not for the small scale farmers. So empirical framework will go 3 steps. The first step, we define the rainfall risk. Identify important rainfall to define rainfall risk with historical data and estimate the impact of monthly precipitation on maize yield and define variations in rain important for maize production as risk. And the second step, climate risk impact was estimated in agriculture decisions and estimate the impacts of the risk index on agriculture practices. The third step, climate risk impacts of maize productivity, and we decomposed the impacts of rainfall risks into decreased detected risk management, means, and other mechanisms. Utilize a mediation analysis, which Soyoka is going to explain later. So the data is the crop yield agricultural practice. We use crop focus survey of Zamstat, and this is a national representative 680 enumeration areas. Each enumeration area has 20 household samples. And the sample size is 13,000 something, but because of the technical problems, it falls below 10,000. With an area under crops less than 20 hectares, it is small and medium scale farmers. And the maize yield area planted, we use district level data, and for area planted, seed variety, fertilizer applied, yield demographics, we use household level data for the year 2020 and 21 cropping season. Precipitation data is from the World Climate Historical monthly weather data and also the Tamstat. Okay.
Okay, it works. So let me dive into the detailed explanation of empirical strategy and the results. So first, we construct risk index. So to do so, we estimate the impact of monthly precipitation on maize yield using district level CFS and precipitation data. So here we consider 3 specifications. The first specification, we include monthly precipitation linearly and additively. And the second specification, we include season level precipitation data to allow the complementarity within the season. So the second specification, we include additionally the interaction term to allow the complementarity across seasons. Okay, so here is the results. So from the first equation, we observe that significant impact on December and January and February precipitation, and especially February precipitation has significant impact on maize yield. And from the second specification, we observe the significant impact on weeding season. Our weeding season is January and February. And from the third specification, the negative interaction term coefficients imply that there exists a complementarity across season. And we see the significant impact of planting season precipitation, but considering this negative interaction term coefficient, on average, this planting season precipitation impact is economically insignificant. So, but still, the weeding season precipitation has substantial impact. So, based on this result, we used the January and February rainfall to construct the risk index. And this result actually consistent with seminal work. So they show that drought in early raining season can be coped by replanting early maturing seeds varieties. But irregular dry spell during the weeding season has a direct effect on crop growth. So as a risk index, we use the coefficient of variation, which are widely used in the previous literature. And we define the coefficient of variation of January and February precipitation as a risk index. And it is important to note that we use a cross-sectional variation in rainfall as an identification variation. So now we are ready to examine the impact of climate risk on the farmers' behavior. So based on the conventional economic theory, we construct several hypotheses. So in the high rainfall risk areas, risk diversification would increase. So risk diversification variable includes the number of planting crops, diversification index called Gini-Simpson index, and number of cultivated plots, and increase the cultivation of drought-resilient crops like millet and sorghum. For the investments, fertilizer inputs that can be considered as riskier investments would decrease, and labor or land investment, which can be considered a safer investment, would the fertilizer input would decrease, but labor and land input would increase. And for the hybrid seed, it is difficult to construct unified hypothesis since, on the one hand, hybrid seed, given the early maturity of hybrid seed, it can be regarded as a risk mitigating investment. But on the other hand, it is high cost. So similar with the fertilizer, it can be risky investment. So to test this hypothesis, we estimate this regression equation. So we just regress the agricultural output on coefficient of variation and control variable. And our interest is the beta CV. This is the impact of climate risk on the farmers' behaviors. And the important note is that we include the previous year's precipitation data so that we control the budget effects and the temporary adaptation to the climate abnormal weather. So here is the results. The upper table shows, the title is the dependent variable. And upper table shows that there is no, actually we do not observe the diversification. And the middle table shows that there we observe the negative impact of climate risk on fertilizer inputs. And we observe that positive impact on the hybrid seed usage. And we actually did not observe the change in the labor inputs, but the interesting point maybe is we observe the different sign of female labor and male labor effects. And we also, consistent with the hypothesis, we observe increase in the usage of the land for farmers. So more specifically, if one standard deviation of climate risk increase, then the fertilizer decreased by 16 kilograms per hectare. And hybrid seed usage will increase 10.6 percentage points will increase. And for the cultivated land also increase about 5 percentage points, but considering that average is already 91, it is not so economically significant, I think. So from these results, we especially focus on the two mechanism and two farmers' behavioral change in the following analysis. So the last analysis that I do is examine the impact of climate risk on productivity. So what I do is I estimate the impact of climate risk on yield in total, as well as mediated by the change in fertilizer inputs and usage of hybrid seed. So the total impact is very easy to estimate. I just estimate the first equation. However, the mediated effects is very difficult to estimate. And typically, usually, the impact of climate risk mediated through fertilizer inputs or mediated through hybrid seed usage is very difficult, and we have to put strict assumption to estimate this effect. So instead of that, we estimate the impact of climate risk conditional on, say, fertilizer usage. So this is called average control direct effects. And there is a 3-step to estimate this parameter, but this is very technical one, so I just skip, and we focus on the identification assumption for the this parameter. So there is 2 main identification assumptions in this parameter. The one is called sequential unconfoundedness, and this means that there is no omitted variable to estimate the effect of coefficient of variation on log yield. It can be more reasonable because the climates can be considered as exogenous variable. But the second assumption is that we can estimate the effect of fertilizer and hybrid seed on we can estimate the effect of fertilizer and hybrid seed on log yield. So it means that fertilizer inputs and hybrid seed is also exogenous. But since fertilizer inputs and hybrid seed is determined by farmers, so it's likely to be endogenous, right? So we conduct the sensitivity analysis in the robustness section. So the another assumption is related to the specification. But if it is violated, the estimate represents the weighted average of average conditional direct effect. So it can be interpretable in this way. So here is the result. So the coefficient actually doesn't mean. So let me consider if the one standard deviation increase in coefficient of variation, then in total, the yield decreased by 22%. But if farmers who are in high-risk region use the same amount of fertilizer in low-risk region, the decrease level declined to about 70%. And when farmers cannot access to hybrid seed, this impact will increase to about 25%. So the right figure shows its estimates of parameter and the confidence interval. So this implies that climate risk itself affects on productivity, of course, because they increase the probability of extreme weather. But this effect also mediated by the farmers' risk management strategy. So we do the 3 robustness check, but we just today skipped here. So now let me conclude. So we do not observe the crop diversification on-farm diversification strategy in Zambia, but we observe the decrease in the fertilizer inputs and increase in the hybrid seed usage and land expansion. And we also see that the climate risk affects productivity in total, as well as mediated by farmers' risk management strategy. So based on this result, we derive 3 policy implications. The first one is that since farmers tend to invest in hybrid seed rather than fertilizer, the market access to the hybrid seeds is very important. So the second one is that second implication is increase the option in agricultural subsidy can be it's better than to really focus on the, let's say, fertilizer, maize fertilizer, and so on. Since as we see that there are many strategies that farms can take, and there is heterogeneity across farmers, so many options could increase the farmers' welfare. And also nowadays, Zambia just provides fertilizer for maize or seed for maize and soybeans. Maybe including more drought-tolerant crops seed increase the farmers' resilience. The last policy implication is that since we do not observe crop diversification in Zambia so far, so maybe promoting crop diversification increase the farmers' climate resilience. So for the future work, we have to refine analysis more, and we can check the stationarity of climate. We can check the measurement error level due to the aggregation of precipitation data. And we also can incorporate the dry spell and temperature effect because we just focus on precipitation effects. So the important question maybe to examine is that why do not Zambian farmers take diversification strategy? So there are three potential explanations. The first is budget market information constraint maybe, or less economic incentive, or strong preference for maize production, or maybe and there is alternative coping strategy, management strategy for climate risk. So thank you very much.
Thank you. Thank you. Thank you very much for the nice presentation. Let's invite Johannes to provide his discussion.
Yeah.
I think, yes, it's a great paper. It's a relevant topic. Can you hear me now? Yes, it's a sophisticated approach. I think the data is good and it's well written. Yes, I could stop here, but then the organizer would ask, why do we pay this guy? So I found something. I think it's you mainly follow the approach by Chen and two other papers. And this is one line of modeling how you could approach this. Another line is, and I think this would be the main critique, you treat farms as a black box here, I think. You don't model any production or technology process. You don't model a lot of specifics on the farm. So this might be something you would build in some arguments in the paper. So why do you treat farms as black boxes? It's a behavioral question in the end that you try to answer. And I think the highly significant time-related variables, T and T squared, this is mainly, as we know, the proxy for technological progress. They're highly significant. And this might indicate that technology and innovation should be modeled in a more explicit way. At least I would address it in the paper to back up some reviews. Then the model quality, I mean, R square is one measure. We know there are lots of measures, but the model quality is not too convincing. So I would also find some arguments or additional robustness checks for the first, not for the last one, for the first two regressions, right? And then with your identification assumption, again, linking to technology choice in some areas might be linked, or for sure is linked to the agroecological context, and might be also linked to some extension campaigns which were limited or were focused only on certain regions. So this identification assumption is critical, I think, for the last, I'm talking now about the last analysis. And then smaller issues, which I can provide you in writing, fertilizer, also a black box, but we all know quality of fertilizer composition is very much related to availability, prices. So these were the main points, but overall it's a great paper and congratulations.
Thank you.
So we take questions.
Thank you very much. We take some questions from the audience.
I think most of them is kind of suggestion. Yeah, of course, I agree that we treat several kind of regression as black box. So I totally agree. So I will more explore about the difference in fertilizer as well, the extension provision in Zambia also. So thank you very much for your comments. Yeah.
Yes, this is a very good presentation and a paper. So I was wondering, is the hybrid seed you mentioned the same thing as the climate smart seed or the climate resilient seed? Is it the same thing? Because in your question, it's the hybrid seed. There's a lot of literature is coming on developing climate resilient seed. So if you can just really clarify the difference.
Yes, thank you very much. Actually, in the data that this information is limited actually. So the information just hybrid seed or conventional or recycle and so on. So it means we do not know the specific kinds of what is, we do not know the specific kinds of, yes, I mean, specific kinds of fertilizer that farmer use. So there is a climate resilient hybrid seed in Zambia as well, but not all fertilizer is climate resilient. So I think it's mixed in the analysis.
Yeah, I think there's a limitation for the Darmstadt data. Crop focus survey doesn't carry those detailed information on the seed, except for whether they use hybrid or not.
Thank you. Any further question? Yeah.
Oh, thanks for the very nice presentation. I'm not an econometrician. My question is related to data use, world climate data. Is monthly average over 30 years around. Yeah, I was wondering whether you use the weather data of the specific year of your measurement make a difference, because this basically the average condition from 1970 to year 2000.
So
yeah. Thank you.
The short answer is no. So we do not explore the different span, or we do not use specific year precipitation data. We just use the long-term average as well as variance of precipitation. Long-term means 60 years. But before that, I tried 30 years constant variation, but the result does not change, so we do not present today. But yes, so not specific year.
Thank you for a very interesting, good study. I have a couple of observations, and then I have also a philosophical point to make that came also up in some other presentations today and also yesterday. So first of all, your observation is a farm, right? A household, right? It's not the county or the district. So here is what I thought. You use the county fixed or district fixed effect. Do you think that you can benefit from having, if you can have access to that data on soil quality? Because you may have in the same county or the same district different soils. So you can increase your R square, which was relatively low for this kind of work, which means that you did not explain a big share of the variation between the observations. So this is one point. Second point, again, this is just for you, depending on your data availability, just a suggestion. And then the second point, you had a comment, again, these comments pick my mind, and it says that you did not see that farmers introduce diversification. And this is, in my opinion, a very important question, because we expect to see, and also in what I presented on the first day, that diversification has a value. And therefore, we expect that in response to water scarcity, to high temperature and shocks, climatic shocks, farmers will introduce diversification, which will provide them with more stability. Now, this is what we expect. I am involved in a big study in California these days on the same questions, on how farmers respond to climatic shocks, to water scarcity, to high temperatures. And what we find over 20 years is the opposite, that farmers, in California at least, move away from diversification, and they decide, or they prefer to move towards more valuable crops rather than to diversify their land use. And this boggles my mind because it does not make sense in terms of, the general theory. And I just wanted, maybe we can talk about it, why in some, but these are very strong, significant results in California, that farmers move from field crops, or the variety of field crops, to perennial crops, and farms just change their land use. And maybe you may have you and other people in the audience that may also get statements about diversification, may have shed some light into that question.
Thank you. If you want to react to that very quickly, because
Yeah. So we thought diversification there, but unfortunately it was not really so. So why they don't diversify? That's the big question. But our observation, we are doing research in southern province, Sinazongwe, Zambia, and very micro research. And then what we have been observing last 15 years is as population pressure goes on, then the farm area becomes shrink, smaller and smaller. And then as a result, people started to monocrop. Diversification is declining right now. So that is a situation because of the population pressure and the household land side is declining. So people don't want to produce a lot of crops, instead focus on the main cereal crop, which is maize.
Yeah, I think that there is several mechanisms that I mentioned. Like also the population pressure as well as like budget constraints. Maybe farmers cannot access to variety kinds of seed, or yes, so it's very important to examine in the future. Thank you very much for your comment.
all right, thank you. I think we can move to the next presentation. Johannes, thank you very much.
Present here some conceptual thoughts that we have more or less completed in our chair group together with the OECD. And they approached us with a question, how can we identify farms that are more resilient than others? What are certain characteristics? How can we target more efficiently, more effectively resilient farms, or farms that show the potential to be more resilient? And also what kind of policy works. So I present here some conceptual ideas that we had, and we have applied this concept to the UK. We currently finish a study on Australia, but here I would like only to talk about the concept, and I'm happy to get your thoughts. So resilience, a brief introduction, what we actually talk about. We use all the word resilience very often, but how do we conceptualize it in order to measure it? And then we talk a bit about water scarcity as a potential shock that we have to consider, and then some methodological hints and data needs. Yes, resilience, as we all know, there is a huge talk about resilience since years. It's the new buzzword after sustainability. And there's even a resilience alliance. And we started to dig out the old definitions and the initial definition of resilience. Resilience, basically, as you can see here, is the capacity of a system to absorb disturbance and reorganize in response to change in order to retain the same identity and performance. This is the main definition of resilience put forward and published by the Resilience Agency. So we find the resilience notion, the resilience concept is very much linked to the systems approach. So it's an entity, a system, a farm, a firm, even an individual that responds to some external pressure. Here we have then the second category in this concept that has to be considered an external event, an external disturbance. And then the system, bounces back and bounces forward. So the system learns out of this shock in order to get more resilient, more prepared to answer and respond to future shocks. And this concept has been mainly developed in psychology and in medical science, and then rapidly adapted and used in ecology. So the first notion is, if we talk about resilience, we have to be clear who should be, which system, which entity should be more or less resilient. Resilience, as I said, is a buzzword, is part of many policy briefs and policy reports. So the EU talks about strengthen the resilience of the farming system and individual farms, as well as the complete food system. The OECD has paid a lot of attention to it, and also the FIO and the Asian Development Bank. But so far, quantitative measurement of resilient systems is actually not much existent. And therefore, this is an attempt to bring more empirical light. I mean, the pressure for agriculture and the food systems are clear. I think they are valid to a certain extent and varying intensity throughout the world. So we have a lot of market volatility that increased, especially Europe, US, Australia. We have a lot of pressure from the society towards more quality-oriented production, animal welfare, sustainable production. Then we have also the problem that in many parts of the world, farm succession is not guaranteed. And we have, of course, climate change that puts a multiplier effect to it, and the pressure to use less and less resources more efficient. So the overall picture is clear, but this is not really, these are pressures that are there in varying intensity. So it's actually not a shock. A shock is something that develops out of the combination of those different pressures. If we check the literature a bit, what has been done in order to quantify resilience, there are some publications that talk about the quantification of certain characteristics related to resilience, but in a more ex-ante approach, so before actually a shock has happened. And there are some studies that exclusively focus on the whole farming system. But so far, no study has really attempted to measure resilience in a dynamic way, in a long-term perspective, and focusing different entities. Basically, we have to ask the question, if we talk about resilience, resilience of what? What is the particular systems, the reference systems that we observe, that we measure? Resilience to what? What is the influence? What is the shock? What is the external disturbance that the system should respond to? Then resilience for what purpose? So why should a system get more or less resilience? Purpose means resource use. So why should we use resources to get a system to be more resilient? And then what resilience capacities? This is the next step we talk about. So if we talk about resilience of a system, what subsystems, what characteristics, functions of a system we actually talk about if you would like to increase resilience? And then, of course, what enhances resilience, policy relevance, what actually works? We talked about diversity. We talked about maybe openness of the system to other ways of management. We talked about, different strategies to get more or less resilient. Diversification is one we have talked about, but it could be also seeking off-farm income, seeking, other forms of even switching the location. So these are the basic questions that have to be borne in mind if we talk about resilience of a system and how can we improve resilience. Then if we take one step further, resilience, which part of the system of a farm actually should respond to a shock in order to increase resilience? And if we relax time, if we also take it to a dynamic perspective, we have different capabilities of the system that have to be considered at a certain point in time. So if we have an external event here, we have the capability of a farm to absorb the negative impact of a shock, a price shock, a drought, corona. Then we have, time goes by, then we have the adaptation phase of the system. A farm adapts in long term to the new overall context conditions. And then some farms in a longer term might transform by identifying new business opportunities, for instance, by significantly diversifying. So we try in the next step to cut the dynamic process of resilience behavior in different phases. And I hope you can see this. This is an exemplary description of the resilience capacities of a farm over time. So this dashed line here is the shock, a natural event, a terrorist attack, corona, a real price shock. Then we have the pre-shock phase, we have the absorption phase, where the system tries to absorb the negative consequences. Then we have the adaptation phase and the transformation phase. So we have clear now that resilience behavior is time-related and has to be, has to be cut in different subphases in order to make sure we capture and describe the type of behavior of the system. But we have also to talk about what should be the indicator of resilience performance. So a system has a certain purpose. This conference has a certain purpose. An agroecological system has a certain purpose. A farm has a certain purpose. And to measure the performance of the system with respect to this purpose, we have to agree on performance measures. Productivity, income, because this is an economic related analysis, but these indicators could be also other indicators. They could be also more related to ecological performance, sustainability. So first, we have to identify the different resilience capacities in terms of resilience, adaptation, transformation, absorption phases. Then we need statistical methods that allow that there was really an impact of a shock. Everybody talks about a shock, 0.0, but in order to measure the response of a system statistically significant, you have to use solid identification strategies. We just talked about it. So the second step would then be to identify if a shock has actually statistically impacted the system. And then in the third step, of course, we would like to know what makes the system more or less resilient. What kind of characteristics help us to indicate more or less resilient farms and more or less successful policies. So we have to agree on how can we measure the performance of a system in terms of economic performance that's not too complicated, productivity of a farm, of a farming sector, income of a farm, of a farming sector. But in terms of other performance areas, if you want, other indicators have to be considered. Diversification, investment, equity, could be also sustainability, but we need a specific indicator that can be operationalized. So we need to make sure that we have a shock that actually statistically significant affected the system in its performance, and we have to make sure that we actually have indicators that measure the performance of the system. One shock could be or should be water scarcity. And then the question is, of course, you know, all this water scarcity, how do we define it? Leads us, how can we operationalize it and how can we measure it? So water scarcity, there are different definitions, but I think indicators, solid indicators for a water scarcity shock, when the indicator for water scarcity has fallen below a certain limit for a certain time, dramatically. This could be an indicator, this could be an indication that indeed water scarcity led to a certain shock for a farm, for different farms in a certain area. You know, there are physical water scarcity reasons, there are also economic water scarcity reasons. This is just more on the specific shock event that we could use here, water scarcity. And currently, indeed, we find statistical or empirical evidence that water scarcity in many areas, the dynamics of water scarcity amounts to certain shock type situations for agricultural production And then indeed we would say, okay, water scarcity could be a shock that we consider with respect to resilience measurement. And then to give you some methodological insights here, first, we would have, and we did for the UK and we did for Australia, we would have to make sure at the sector level, covering all farms, that indeed we can say that the water scarcity shock had indeed a dramatic impact, a significant impact on the performance of those farms. Because we have many other events that are taking place over time, price events, policy events, other events that could also lead to a performance increase or decrease of those farms. Then the second step is that we do a dynamic analysis at the farm level, and we then try to identify the performance of the farm system in response to this shock over time. So actually closely looking and considering measuring how the farm performed during the absorption, adaptation, and transformation phase. And then, of course, this is where policymakers are most interested in what characteristics can be significantly identified that show us, okay, this could be a farm that should be targeted with resilience policies. The resilience effect would be most significant for this type of farm. And then at the sectoral level, policymakers are interested to have a kind of resilience index where they could just have a kind of, a very rough indicator how the sector, the overall sector develops in terms of resilience with respect to certain shocks. So this is the better of analysis that we have applied for the UK and that we currently do for droughts in Australia. And we also have plans to apply this for wildfire shocks in Australia. I also have talked with Japanese colleagues who might be interested in doing this sort of study. Yes, I'm not sure how much time I have, but okay. But I can save time for others. Some methodological hints at the end. I don't have an empirical application here, but we can send you the discussion paper. So you have to make sure that we actually measure what we like, that we actually identify empirically what we like to see. So we talk about resilience, but as I tried to outline at the beginning, resilience is linked to a shock. If we cannot make sure empirically that the shock actually affected the system farm, then we talk about a general dynamic, but not on a resilience shock behavior causality. So first is the analysis at the sector level, and therefore we have different batteries of regression analysis. If you can read this all on your own. And then, these are the different methods we would use. So we would check that there is indeed a structural break due to the shock at the sector level. Then we would reaffirm that also at the individual farm level, we have an effect by this autoregressive, autocorrelated distributed lag model here. And then we would ask the question, what kind of characteristics can we identify that, that make more resilient and less resilient farms? This is related to a shock. This battery of analysis is related to a shock that cannot really be located in its effect. So for instance, the drought in the UK was a more regional phenomenon. So there is no real data and no real evidence where we can draw the line along the drought affected, the shock affected sector, the shock affected farms. So this is the approach that you would apply if the spatial identification of the shock affected entities, farms, cannot be completely done. There is another approach that you would use if you would like to investigate the resilience behavior at a higher aggregated level, say districts. We just talked about districts or municipalities. Some of you know this approach. There's a synthetic control group approach where you look for more or less the same districts, municipalities, and then you build a counterfactual group around these synthetic groups, and then you measure the impact of the shock. And finally, there is the old traditional, still valid difference and difference approach, and this is very much at the system level, at the farm level. When you really can identify this farm has been affected by a drought or wildfire, this farm has not been affected by a wildfire, and you have really spatial
spatially reliable data. Then you would do a simple matching approach at the beginning. So you match farms that have been affected by the shock, by wildfire, to farms that have not been affected by wildfire. You look what has happened before, after the wildfire, you know, this double difference approach. And this would be then approach that you apply if you try to analyze the shock impact at the farm level. So 3 different approaches, considering the specifics and the data availability and the spatial identification. Yeah, and then finally, policymakers are very interested in this combined resilience index, and we estimated this index at the individual farm level over time for the UK with respect to drought shocks. Basically, it's a resilience index that is built of different scores, resilience scores for each farm for all different resilience phases. So we analyze how successful is a farm behaving in the absorption phase, in the adaptation phase, in the transformation phase, and then we build an index out of this. And those farms that score very high on this index could be farms that should be targeted with resilience policies. Or if you would like to support those farms that are of low potential with respect to efficient, effective resilience adaptation, then you would target those farms that are have a low score. Data needs are very intensive, and I would be happy if you have interest to conduct a repeated study in some of your countries, but we would need a panel data set. We would need data before the shock and after the shock. I've shown you the different the time frame. But I think farm accounts data is available in many countries. It doesn't have to be full balanced. It can be also unbalanced data. Yes, these are the conclusions, but I think to give you a more significant conclusion here. So what I like to show, or what we like to address in our research, resilience is very much a buzzword. It's rarely robustly measured. So measured, you can measure everything by some measures, but it has to be significantly, statistically robust. The system perspective is key. So first you have to ask the question, what is the system, the economic, the ecological, whatever system it is that you would like to analyze with respect to resilience? Then you further break down the capacity of the system. So the system has a capacity to respond to this shock. Data intensiveness of our approach, this is what you have seen. Water scarcity, as I try to have outlined, is one shock that can be conceptualized, but you have to make sure that the indicators actually show that there has been a significant change with respect to the dynamics, the long-term development of water scarcity. Identification strategy is key with respect to investigating, making sure that the shock actually has affected the resilience of the system. And then, yes, less talk and more measurement is required. This is something which is very important for imperial economists. So I think we need to make sure that we not only talk about resilience, but also measure it in a statistically significant way. Thank you.
Thank you, Johannes. Let's invite Daiju to provide.
Okay, thank you very much for your presentation, Johannes. And so this is kind of conceptual presentation, but in fact, the paper so includes a lot of statistical analysis, right? And so that's I think I like the idea. So because so there's a lot of talk about resilience, adaptation, coping, but so this approach kind of makes it kind of quantifiable and could be translated in real statistical analysis. That's what I liked. And so it answers certain questions, but it doesn't, so answer some other kinds of questions. And so one thing I noticed is that so this is a statistical analysis, and it doesn't, so you focus on the productivity or income as you explained, but so there's no explicit, so the intertemporal, so the evaluation of net benefits, right? And so that's, so that's because of that, so we don't know exactly. So, so the responses of, for example, farmers are really optimal or not. And that is, and so so that there's 3 phases. And so the absorption, adaptation, and the transformation. And so this concept kind of assumes a transformation is good, probably. Transformation is good thing. But so I'm not sure. So because for example, you did analysis on the UK farmers, and so it somehow relates to Ariel's comment for the last discussion, but in highly developed country and the highly developed agricultural market. And maybe some farmers, high-end farmers, highly profitable farmers kind of choose to focus and not to transform intentionally. So that's so that kind of mechanism is not known through this the analysis, and that's might be one thing. And another thing is, so as a Japanese, and so there's the applications made for UK and also Australia, I guess. But so we are very familiar with kind of large disasters, so extremely large shocks. And so your approach is based on kind of individual responses, right? So farmers or maybe individual sectors. But so what happens after a large disaster is really, the society changes quite radically. And so maybe, so the market itself might, transform, society might transform. And if that's the case, it's hard to, identify. So by focusing on productivity or income. Yeah, but yeah, so those are my comments, but I enjoyed your presentation also, Chris.
Thanks, Daiju.
No,
would you like to react to Johannes?
Respond now, or what's the plan? I think, thank you very much. They're very good papers. I think comments. Transformation, indeed, you assume that transformation is a good thing, but and this also links to what you said about the changes in the context. I agree. So if the context changes to a more positive, advantageous environment, maybe the adaptation and transformation might be not necessary or goes in a different direction. I agree. Yes. Thank you. Thank you.
All right. Let's open up and take 1, 2, 3, 4. Yeah, Eric.
Thank you so much for the presentation. So I was just have a question in terms of the natural system perspective. When we are talking about resilience, there is an ideal system state that is in equilibrium with the condition. But when we are talking about natural human system that is very dynamic and unpredictable, I wonder whether when we are talking about resilience, because these systems may not be sustainable, or maybe it's a farmer that is already polluting the river. So do you need to basically include the definition of that ideal system state that you want that farmer to be? Or because sometimes it's good that that system, if it's not sustainable or polluting, actually to crash. So we don't want them to be resilient because they have unsustainable practices. Just a thought. I wonder whether that is considered.
Good point.
Thank you.
I think basically it's the definition of resilience, and resilience, we defined it or try to find economic indicators. You can also find environmental sustainability indicators. And the second question was the ideal. I think the ideal system, that's a static question, and we live in a dynamic world. So the ideal system is constantly, I mean, it's a system that in our notion is highly sustainable, but also productive. Gesundheit auf Deutsch, and but is able to adjust to whatever dynamics we have. But this is what the policymakers, I think, should and want to identify systems that are more efficient, more effective in using public funds to get more or less resilient, adapt to whatever change in the dynamic system emerges. Yeah, well, you're not an economist, you use equilibrium. Okay, that's fine for us. We have always problems if we use equilibrium, but of course, yes, in a kind of resilient equilibrium, if you want to.
Oh, good. Thank you. I'd love to read the paper. I found that really interesting. My comments kind of follow on. I understand why you're modeling the concept of resilience, but you're really modeling financial viability. So yeah, I think it's a term issue. Like, for example, if I think about resilience, like we've just modeled suicide rates, right? If people were killing themselves, it's obviously a huge social problem. You know, it can be linked to droughts. But we also know in rural areas that financial viability is one of the main drivers of, if they're not viable, farmers are killing themselves. All right, so I understand there's a strong link between financial viability and resilience in lots of different areas. But I think if you're going to use the term resilience, I think you're much better using a proper term that actually you're only modeling productivity and farm income, which is incredibly important. I think call it what it is and then link it to resilience in all its different forms.
No, I fully agree, but we haven't. I mean, these are just examples of resilience indicators. Could be productivity, could be income, could be also financial assets, could be a sustainability indicator.
Okay.
So this is the performance of a
paper, but yeah, I mean, what I saw, productivity and farm income, like I wouldn't call it resilience, I'd call it financial viability. The other
but that's the indicator for performance of a system. The question is, how would you best characterize the performance of a farm system? Could be financial viability. Would have to find a ratio for that, or could be relative productivity, or assuring a certain level of income. And if you say, okay, resilience more in the context of environmental resources, then you find a sustainability indicator, water use per output unit. So these are just two examples.
It's problematic. I'm saying there's lots of problems. I'd love to get into, read the paper and we'll have a big discussion, but lots of problems there. Just another technical question. So you're saying you're doing a panel both at sector and farm level. With ABARES data, you've got a maximum of 3 years. So in terms of following the transformation of a farm, like I can't see how it's happening in the actual data, that's all.
Yeah, that's the main weak point of this analysis, the definition of the subphases, right? So absorption could be 2 years, 3 years, 4 years, depending on the shock, then 2-3 years adaptation, 10 years, 2 years transformation. So this is something you have to, that's the weak point. You have to base it on expert knowledge, on the type of the shock. So for droughts in Australia, we had a look on the data and said, okay, a drought, there's some repeated droughts of 2-3 years for the absorption phase. Then we have another 2-3 years for the adaptation, and then 2-3 years for transformation. And indeed, we find some significant change over, but of course, this is, you could also say transformation phase. I define it very long-term, 10 years. Yeah, these are.
We have a brief question from Eric.
Oh, thanks very much for the presentation. And I appreciate the challenge of anytime you try to take on the word resilience, given all the different meanings for all the different disciplines. So I thought it was at least a good approach given the target of the, like, sort of the mission of the research. I was going to go back to the you mentioned sort of the ecological systems theory, thinking around resilience with Holling, and there's also an origins and mechanistic thinking around engineering resilience, where your whole idea is to come back to the normal. And I think it gets to the comments of the discussant in here. It might be helpful to provide policymakers just some feedback to recognize that does happen, and that there's a resistance to change, and that can be for, you might be able to work political connections, or at a national level, there's subsidization that happens that actually inhibits resilience and transformation if you think that's a normative good. So if it's not obviously not the focus of what the intent of the end analysis is, but it might be worth at least touching on, especially if you're going to have it in academic literature.
Yes. Okay, thank you.
Thank you. Can we scratch a bit or we stop? Okay, 1 minute. Okay.
Yeah, I think my few comments is based on our work we are doing. We were actually calculating resilience, with and without. And I think the methodology, we thought of using an econometric model, but then we thought something do it which we can communicate very well with the policymakers. And here we are using the extended version of the policy analysis matrix, where we have one, the traditional one, and one with the climate smart or regenerative and all that. And we are basing our results on economic criteria and technical criteria. Economic criteria, financial and economic profitability. I think it's a lot more easier for me, and I have few copies. If anyone wants, I can share it.
Yes, maybe we can collaborate then.
All right.
Thank you.
We have Linus.
Thank you very much. When you started talking, something immediately jumped on my mind. There is a book written by Nassim Nicholas Taleb. He's originally Lebanese. The title of the book is Anti-Fragile. And his argument in the book is basically that we should not be afraid of shocks because they make us stronger. He has a financial background, I guess. To the comment on whether or not it's sufficient to focus on profitability or productivity, I think for me, the way I see this is more that you are doing some sort of partial equilibrium analysis, which we do a lot in economics. That's one way to think about this. But not to take longer, what I wanted to recommend for you is there was a question on whether or not you are really able to identify intertemporal effects. There is a newly developed generalized diff and diff,
yes,
which means you can study the effects of shocks on the same farm over time.
Repeated differently.
Right. So just wanted to point that out.
Yes, yes, we try to apply this in Australian case, but this is based on the availability of repeated observations in the data set, and farms have to leave. I think in many countries have to be replaced in a farm accountancy survey after certain years. We need a certain amount of follow-up years for each farm to apply this approach.
All right, let's move to the next presentation, which is given by Daiju Narita.
I think it's working. So first of all, so I need to note two things. So before beginning this presentation, so there are several authors. So for this paper. And so the first author, Ife Aina, is actually did the the heavy lifting work, but I happen to be the presenter, and he's not able to come here. Unfortunately, he plans to come. He planned to come, but he wasn't. But yeah, so I hope I managed the presentation. So that's one. And another thing is this is a still work in progress. And so I'm going to present some numbers, but so that are still subject to change. And in fact, so we kind of exploited, made use of this occasion for research discussion on this paper. So it's still developing. And so this paper is on the Limpopo River Basin, so on South African part. And so you might wonder why I from Japanese is so this thing, so presenting a paper on South Africa. So here, and so let me explain that's the context. So this is part of a research project that started last year under the so as a collaborative project between Japan and the African countries, including South Africa, and it's called AJ Core. And actually, Chieko is so the supervisor so of the program, and so for our project, so we have so UCT and the University of Tokyo and other members, and so yeah, through that project, so we focused on the Limpopo River Basin, and so did so on this paper, so did some simulation studies. So that's the context. And so the Limpopo River Basin is very interesting case. And so because so it relates to some of the challenges we face, and we need to analyze it in an integrated way. So for example, climate change, water scarcity, and urbanization, industry, agriculture, so impact on food security, environmental health, and so there are some of the agricultural activities and mining activities that means pollution. And we need to analyze those problems in an integrated way. So that's something we're interested in. And as I said, the Limpopo River Basin is a very interesting place, interesting area. So first of all, it's an international water. So the water resource, so the water resources used by South Africa, Botswana, Mozambique, and Zimbabwe. And so that it's used for irrigation, and the resources are shared by over 18 million people. So it's a lot of people. And yeah, so also a population is expected to increase. And here's the map. So here, so this is South Africa, and this is the Limpopo River Basin. And so this map is the South African site, which we focused on so for this particular study. And so here, so the so water is used as a drinking water, and the mining activities use some water, and so water is used for irrigation as well. And so the mining activities so cause so pollution, so acid pollution like sulfate, and so there's also agriculture pollution, so like nitrate or phosphate, and but also there's a problem of issues of water use, water allocation, and so those need to be assessed somehow. So that's, and for that purpose, so economic modeling, hydroeconomic modeling, like the one so we're doing, should be useful. So that's the motivation for this study. And so, yeah, so the research objectives, so assess water allocation and economic impact of pollution abatement solutions using hydroeconomic modeling, rather, so as I explained shortly, rather like a simplified framework, but it includes the component of so drinking water and agriculture and mining. And we examine policy options for sustainable water quality management of the Limpopo River Basin. And yes, so to contribute to policy discussions. So that's our objective. And so we do, for that purpose, so we constructed a simple optimization model to analyze that. And so that, but it integrates water quality and scarcity patterns and the economic value derived from different water demand sectors. And integrates hydrology and economics and climate stress and some institutional and infrastructure constraints as well. And so these are equations, but so perhaps so we should start with this figure. So there are some components. So the hydrologic component, and so the water, so the model water, and water supply. So comes the industry sector and the urban sector, and the water is used, but there's some return flow with some pollution, and so that goes to environmental component, and so there's some explicit so estimation of pollution load and economic costs from it, and so that's basic. And for so in this component, so there's so water used by people, drinking water, and irrigation water used by agricultural sector, and the mining.
so this is the radius for the state. And so the set, so there's an economic component, and so the water is used so in the drinking water and also the mining sector. So that is represented by kind of the standard supply assumption. And so whereas so on, so assume some different types of crops and or types of farming and for each so that's the demand and some cost. And to the mining activity and the agricultural activity leads to pollution load.
Okay. It's good now. So should I repeat? No. Okay. Yeah. So so actually so the for the agriculture component so there's no like demand supply mechanism working so because of so the water regime so the allocation of water rights in that region. So in this sense so the model representation formulation is a bit different from this. And hydrologic component, so there's the water, so coming, so they're coming out and coming in, and the loss, and also so the water used in the urban sector and agricultural sector, and but so those so so the uses water come back to some proportion come back to the flow. And so that's so it's a return flow, and that includes pollution. And so there's some amount of water for so river integrity. And so that it's not so clear from this figure from the slides, also in the paper as well. But so there's some spatial so disaggregation. So that's the meaning of subscript D. And overall, so there's a so benefit of water use and pollution damage cost, and so that's is optimized, maximized. So that's the model structure, which is quite different from, for example, more comprehensive CGE modeling. So there's no so there's no some modeling of finding the price, equilibrium price, and so the market clearing. But here, so that simply so benefit and cost, and so net benefit is maximized, is somehow so water allocation is made. But still, so the different policies and different so conditions so return different results in terms of water pollution and the costs. And so what we examined is 4 cases. So the first hypothetical case where so some pollution polluter pays principle so instrument is introduced, so to reduce pollution. So by so the agricultural sector and also the mining sector. And so that's policy 1, and policy 2 is on agriculture, irrigation efficiency. So that's policy 2. And so 3 is also so the on agriculture and manure treatment plants. And 4th one is mining wastewater treatment. And for each, so actually there's some so implementation costs, and so that's not actually shown on the paper in the paper yet, but there are some estimation. And so so these are components, model components, and so these are 4 policy scenarios, and also so we considered, we analyzed so the water stress scenarios, so which is a normal case and a moderate so drought case, 30% reduction, and so severe drought, 60% reduction. And so estimated, so computed the costs and water allocation and also so pollution so loads. So that's the design of the model. And so that for the yes, so indeed, so this is a quite so the complex model, and so it's hard to explain everything. But so here, so we included so many elements in the models. For example, so the few crops, horticulture, fruits and vegetables, and different kind of irrigation, and so livestock water use, and also different kinds of so water pollution, so the phosphorus, phosphate, nitrate, and sulfate, so these things. And so for each so normal climate scenario and moderate drought scenario and severe drought scenario, and so water use and the pollution load were computed. And also, so sectoral benefits of environmental damages under drought conditions. So these are, so median rand. And so these are the numbers. I don't explain it. And so even a smaller so numbers, but so this is like results for policy policy scenarios, and without policy, and policy 1, polluters pays principle, irrigation efficiency, and so manual treatment, and so mining water treatment, and for each so pollution, so the conditions, and also so the private benefits and the environmental damage and social benefits were computed. And by the way, so environmental damage, so how to quantify the environmental damage? So in economic terms, so that's also up to scrutiny, I guess. But so in this case, so we just assumed so environmental pollution would be so the eliminated by treatment, and treatment costs are so basically environmental damage costs. And so for each so a policy scenario, so we analyzed a severe drought condition and the normal conditions. So there are 4 times 2, 3 cases. But I just so present some highlights of the results. And so first, so the case of polluters, polluter pays principle results. So that's quite expected results, but so introducing some pollution mitigation policy, so paid by polluters. So of course that's it reduces so the profits, but of agricultural sector and the mining sector, but social benefits increase. So because of the reduced environmental damage. And so there's some impacts under severe drought as well. And so that's these are the numbers. And the irrigation efficiency, so it's similar results, but so focusing on so agricultural sector, so that's these measures. And so the normal climate conditions and the severe drought. So these gives somewhat different results. And so manual treatment plants and also wastewater treatment so results. So these are also targeted so policies. But just briefly showing so that although so that it's quite targeted so the policy so that it's compared to so it gives some benefits, and it's a probably quite viable policy. So that's as a suggestion of the results. So all policies seems to be effective so in reducing water pollution in the Limpopo River Basin. And so what is interesting, so from this analysis, somewhat expected, but so the different policies are good. So for different climate conditions. And so some policies are good under normal climate conditions, and some others are good under severe drought conditions. So that means, so maybe it's some kind of policy mix. So introduction of some policy mix is so favorable. So that would be one implication. But I would say, so this is, as I said in the beginning, so this is still work in progress, and the quantitative results might somewhat change. So general, so there, at least there seems to be some general policy message out of it. So that's all.
Thank you. We invite Chieko to provide the discussion.
Could you please put up the slide? My name is on the top, Umetsu, UMETSU. Okay. Okay. Oh. Thank you very much. So, Daiju, thank you very much for your presentation, and the paper was very well written, and I was pretty impressed by the result and the framework you guys developed. And this is just a summary. I'm not going to repeat, but the last one is I want to stress that the paper shows the trade-off between the water scarcity and the pollution. So that is expressly given by the numerical analysis. So that was a very nice result, I think. And overall comment is this paper utilizes the integrated approach, which is very good, integrating by the hydrological, economic, and pollution aspect, and which is, I think, very unique in African context. That because the data availability is a limiting factor to do this kind of work, and also the purpose of the paper is rooted from the society's emerging social, economic, and environmental needs, which is very important, I think. And optimize the model they developed is very tractable, very easy to understand, and for policymakers to understand the structure, it's very easy. And the result they provided, the simulation result, the maximization result, is very useful for policymakers to understand the cost and benefit of water use and resulting environmental consequences. I had some questions, and in the paper, the cost, how cost is included in the model is not explicitly written, although there's a description. So but Daiju already explained to me in the presentation that it is included, in fact. So thank you very much. And what I couldn't understand is water charge included in the model, because water saving technologies will affect the water cost, total water cost will decline. That those farmers can save the cost of production. So that part I couldn't understand the model structure. And after comparing for policies, which options are recommended for Limpopo River Basin? Also, I think in the paper it's not explicitly written which one to recommend in which situation and why. So I think maybe in the conclusion, maybe you can elaborate further. I think you already presented it in addition to the papers. And they make two simplified assumptions, which is okay, but is there anything else you can do? One is constant input and output prices, and another is assumption that the yields decline linearly with an expanded scale of production. So I think the theory says that it's more like increasing the yield as area expands and then declines. It's more like an inverted U-shape. I think it's not totally the decline. And lastly, the dynamic implication of the model. I think this model is static. There's no time, I think. So my understanding is you try to express dynamic interpretation with a static model, if I might be wrong. So that may be okay for short and mid-term model, but I think it may be interesting for policymakers to do a long-term perspective and what would be the dynamic adjustment in case of water scarcity. Because if you consider dynamic setting, more different variables must be coming, like population pressure or different technology, something like land use changes, and maybe alternative crops, more water saving technology, or even alternative water sources. So maybe this is current model is pretty short-term or mid-term perspective. So, but long-term perspective might be another way to go. Thank you very much.
Thank you. Thank you very much. Would you like to react to those points, Daiju?
Yes, thank you for the comments and all, so the be taken. And so for the future research, so that's something, so we've been exactly discussing, so last couple of days, so including some temporal dimension for the future research. And also, so perhaps I should mention, so one thing, so about the costs and also, so water, our model formulation of, so on agriculture. And so it assumes, so that basically, so irrigation area expands. And I think maybe GB can, so give a comment as well, but it reflects actual kind of, so water system in the area. So it's not that there's no really, competitive water market, and so that there's a water right allocated to farmers, and it's quite rigid. Right? So it also the case that so there's some potential for further irrigation. In my understanding, I have visited that area once, and so that's what I heard. So it reflects, so the agriculture sector, so model formulation reflects certain kind of realities, so in that region, I think. And do you want to say anything? No?
No, I'm fine. I mean, this is sorry. You want me to react?
Yeah.
Yeah. Yes, no, that's fine. I was saying the points you raise here, they are valid. We run the simulation with static data. I mean, you are right. We're still thinking about how to make it dynamic depending on data availability. And here in this particular context, the main idea was, for instance, to provide a simulation of different approaches, not only in terms of optimizing water use in different sectors, but also maintaining a good quality of the water. I mean, in the economic literature, how water quality is modeled, if it's not through collecting data, is quite debatable. And therefore, there is still, some reading going on. But through shadow pricing mechanisms, introducing more efficient technologies in the irrigation sector, providing some subsidies to the wastewater treatment plants. These are parameters that will be included in the model to see, how far the simulation can go, right? I think Christina has a question.
Thank you. It's a more general question across some of the presentations, and I've noticed that the term water use has been used a lot. And I think also more specifically, water withdrawal or water consumption is helpful, especially when you think about perhaps different types of irrigation, flood irrigation, drip irrigation. And I'm curious if, like, in these types of research, is there that distinguishing ever made? And if so, what kind of consequences might come? And I noticed, is it like residential, agricultural use? So yeah.
Yeah, so different type of irrigation technologies. There are included, although, so it's not explicitly presented, but yes, so we considered these differences as well. But yes, so maybe that's a, so the one point we need to stress in the paper. And thank you for the comment.
All right, thank you for your presentation. When I look into your benefits and costs, what I saw that both the mining sector and the agricultural sector will have costs. And that's really strange. I mean, there is no win-win solution. I mean, how you would be implementing such measures if both the mining sector and the agricultural sector are losing money. And the other thing is that the costs to the mining sector as horrendous, are very high. And I wonder why is that, and what kind of mining sector you have been considering, and if you have considered different options, different alternatives for the polluter pays principle. So what kind of technologies you have been considering for that?
Yeah.
So these are my two main comments. Yeah.
Thank you. Thank you very much. So that's these are good points. And so first, mining. So the costs. So costs may be high in these results. And yeah. So at least in the model. So it is still kind of feasible result, and because it kind of assumes so water is allocated by kind of invisible social planner. And so in this way, so that's feasible. But so in reality, of course, if the costs are too high for those industries, that could be problematic. And that's something so we need to think well. So in the interpretation results, I think. So thank you. And so for the mining sector, so it's there's no specific industry so we had in mind, but so we did calibration, so based on some statistics, and mainly so as I understand, correct me if I'm wrong, but mainly so those areas gold mining is so what is taking place?
Yes, we have been asked to stop. Then unfortunately we have to, or fortunately, it depends. We're coming back after our coffee break and we finishing our last session, right? I hope you don't mind. Okay, then we see you in a bit, in about 10 to 15 minutes.